Okay, we're on chapter 8. We started talking about gases, I believe. So last time we talked about gases, and obviously that's the state of matter, as we talked about, where everybody is completely broken apart from one another. They're flying around. There's collisions that are occurring as these gas molecules are flying around, which results in pressure that we associate with gases. We talked about three important units of pressure that we very commonly come across in this class, and that is ATM, which is an atmosphere, mmHg, which is millimeters of mercury, and torr. And these, I would say, is probably your big three in terms of units for pressures that you'll probably see. The relationship between these is 1 atmosphere is equal to 760 millimeters of mercury, and that equals 760 torr. And that is because 1 millimeter of mercury is equal to 1 torr. It's a 1-to-1 relationship in terms of the conversion. So not too bad to convert that. You just basically just change the unit. The number stays the same in that particular case. We started talking about some gas laws here. And really, when we talk about gas laws, pressure, volume, and temperature are 3 sort of variables that we deal with a lot with gases. And in a lot of gas laws, some of these are sort of kept constant. Other ones are changing. The first one we looked at was Boyle's Law. And Boyle dealt with pressure and volume and kept constant temperature. And Boyle V1 is equal to P2 V2. Here, the pressure could really be any unit you want as long as they are the same units of pressure on each side. And same thing with the volume here. They also can be pretty much any unit you want as long as they are the same on each side. The relationship that we see with Boyle's Law is as the pressure goes up, the volume goes down. So sort of a opposite relationship. And as the pressure goes down, the volume goes up. The relationship there really is, when we have a very small volume, we have obviously our gas molecules in a very small location, which means it's not going to take very long for collisions to occur. And we would expect an increase in the number of collisions and thus an increase in the pressure. And that's different when we have a larger volume. Gives everybody a little bit more room to fly around in. It's going to take longer for collisions to occur, and we have a less pressure associated with that. Any questions on that there? Okay. So then let's continue on here. The next sort of gas laws we're going to talk about is Charles' Law. Charles' Law dealt with the volume and temperature relationship. So Charles' Law dealt with volume and temperature and held pressure constants in that situation. And this is Charles' Law right here, which is V1 over T1 is equal to V2 over T2. And again, this is at constant pressure. There's a similar relationship, which is sometimes referred to as Lussac's law. And that is P1 over T1 is equal to P2 over T2. This would be at constant volume. So when we look at sort of the relationships that occurs here in each of these situations, in terms of the pressure, the volume, and the temperature, let's first take a look at the relationship that we see when we basically graph any of gases here. So if we graph any of these gases, and you take the temperature line all the way back to the temperature axis, they all pretty much hit the exact same spot, volume versus temperature, which is sort of a Charles' Law plot. And that spot is minus 273 degrees Celsius. That number should look familiar. That's the number we use to do what? To convert to Kelvin. And if you convert this to Kelvin, you add a 273 to it, you get 0 Kelvin, which is known as absolute zero. And Kelvin recognized the relationship of this for gases. And ultimately what that means is, as we'll see in all these gas laws, if you have temperature like we do in these two here that I just wrote, it needs to be in Kelvin. And it does need to be in Kelvin, regardless if they give you the temperature in Celsius and they want you to give the answer in Celsius. You need to convert it to Kelvin and go into the gas law and then convert it afterwards. So sometimes people, when they do these type of problems, they'll go, oh, they gave me the temperature in Celsius. They want the answer in Celsius. So I don't really need to convert it. I could just put it into the gas law and you will get the wrong answer. So you definitely always pretty much any gas law, just convert the temperature to Kelvin is pretty much what you always need to do in this situation. So let's talk a little bit about these relationships that we see here. We'll start with over here, Lussac's law, which is at constant volume, which means that we have really a container here, and the volume of that container is not going to change. It's basically fixed, which means when we have our gas molecules in there, for example, and we decide to increase the temperature, will the gas molecules move around slower or faster? They will move around faster, which is going to lead to more collisions. And because the volume is fixed, we will start to actually see the pressure go up in that situation. Because they're moving around faster, there's going to be more collisions. Opposite is true if we lower the temperature in that situation. Gas molecules are going to be moving around a lot slower. We're going to have less collisions occurring, and we will see basically the pressure start to decrease in the situation where we have really a fixed volume. Now, when we get to Charles' law over here, this volume is not fixed. This volume can move, but we want to keep it at constant pressure. So what happens is in this situation is if we increase the temperature in this case, as we just talked about over here, and the volume did not move, we would expect to see an increase in the number of pressure that's going to happen because of the increase in number of collisions. But because we want to keep it at constant pressure over here, what actually happens is because our gas molecules are now moving a lot faster, we actually will see an increase in the volume. And that increase in the volume is going to allow those gas molecules basically to have the same number of collisions, if you will, as they had in the previous volume. And that's what's going to allow it to keep the pressure constant. So in the case of Charles' law, the way it's able to really maintain a constant pressure is the volume of the container will actually adjust based on the temperature to keep the number of collisions relatively constant. And the same thing will happen if we lower the temperature in a Charles' law situation. If that volume doesn't move, we would expect basically to see a decrease in the pressure. But what happens when we lower the temperature, we will actually see the volume actually start to go down as well. And what that's going to do is shove all the gas molecules together, and that's going to keep the rate of collisions up, and that's going to keep our pressure constant. So in the case of Charles' law, it's able to maintain that constant pressure by adjusting the volume. And we can't see that with Lussac law because the volume is fixed. So there's no adjusting of the volume. So when we raise that temperature, thank you. When we raise the temperature or lower the temperature, what we end up seeing is an increase or decrease in the pressure. Any questions on that there? Now, in terms of our equations here, the volume really could be any unit you like, as long as, again, they are the same on both sides. As we talked about before, it does need to be Kelvin there for our temperature. The pressure over here, same deal, can be any unit you like as long as they're the same. But once again here, we do need it to be Kelvin in terms of our pressure. Any question on those relationships or those gas laws there? All right, so that's what we saw there. Let's try one here. In an experiment, 452 milliliters of a gas is used in a light bulb. It's heated from 22 to 187. What is the final volume here? Take a moment and see what you get. Okay, so let's take a look. So as I mentioned last time, especially with gas law problems, a lot of times it's a good move to sort of pull out the information, label it, and a lot of times it'll sort of point you in the right direction in terms of what gas law you might need to use. So obviously here we have a volume that's 452 milliliters. It's got a temperature of 22 degrees Celsius. It goes to another temperature of 187, and we're looking for a final volume. So now we got a few to choose from here. You can kind of pretty much see that Charles Law here is really the only one that would make sense, as we have no pressures for the other ones. So clearly we can't use those guys. We do need to do a little bit of work here as normal. Pretty much should just be an automatic temperature to Kelvin when you're doing gas law. So it just should be like the first thing that you do. We again are going to add a 273 to each of these to convert them into Kelvin. And if we do that, it looks like a 295 Kelvin and a 460, I think, here, Kelvin in this case. Now that we have it in Kelvin, our volume unit doesn't matter, but when we do solve for it, we will end up with milliliters at the end, since that one is in milliliters. So we could call the first ones ones and the second ones twos, if you like. So we'll do our V1 over T1 equals V2 over T2. In this case, we're looking to solve for V2, which means basically we need to take T2 to the other side. So again, the quick way to do it when you have an equal sign is it will end up in the opposite location, just kind of above on the other side. So V1 T2 divided by T1, and essentially we're multiplying by T2 to both sides, will equal our V2. So now making sure we do put in the numbers in the right location there. Going to give us 452 milliliters. We have 460 Kelvin divided by 295 Kelvin. Once again, here our Kelvins are going to cancel. That's going to leave us with milliliters. And a little dividing there. There we go. We'll go with 705 milliliters in this case. Now, once again, we can think about sort of the relationship that we see in Charles' law. In this case, our temperature went up, which means we should expect the volume to also go up with it. And it did. It started at 452 and ended at 705. So again, it went in the right direction. And sometimes that's, again, a good thing to kind of look at to make sure, you know, maybe it didn't invert a number or something like that. Any questions on that one there? Yeah.
We don't take the 460 as the first exact number, correct?
Yeah, so technically you would look at it. I would look at it like that. Technically speaking, it would end up at a whole number, which in this case would be 460. And I probably would maintain it as like technically 460 with a decimal point, because it had kind of three significant figures to start with. And that's what I would sort of keep it at in that sense. But yeah, it is. You're supposed to do with temperature conversions, just make it look like the original number. And in this case, you know, we basically ended up with three significant figures on all those sort of values. So that's where we ended up in that case. But yeah, other questions? Yeah. Would I change it to Kelvin for both temperatures? Yeah, you should always do that. So pretty much there's no gas law that you use where you would use Celsius in it. So it always needs to be converted to Kelvin. So as I mentioned before, that should just be like when you're doing a gas law and you got temperature, like one of the first things you do is just like get it into Kelvin. And again, sometimes people always miss that part or don't do that part because, like I said, there's a lot of problems where they'll give you the temperature in Celsius and maybe ask for a temperature in Celsius. So again, people think, well, I don't really need to convert it because I'm trying to get the same unit at the end. But you absolutely do need to convert it when it goes into any gas law, pretty much into Kelvin. Other questions? So putting things together, including one other one, let's talk about our friend Avogadro. Why not? Avogadro, he had a law, a number, and he wanted a law. So when we think about Avogadro, right, we think about what that is, moles. Yeah. So not surprisingly, Avogadro's law deals with moles. and that is V1 over N1 equals V2 over N2. And this is actually a constant pressure and temperature. V is volume, and again, it could be any unit you like. N is actually the moles. So obviously here Avogadro's law deals with moles. And really the relationship that we see with Avogadro's law is as the moles increase, so there's the volume sort of proportionally. You kind of do stoichiometry actually in an Avogadro's laws relationship if you have all gases, instead of doing a mole to mole relationship. If it's constant pressure and temperature and everybody's gases, you could actually do a volume to volume relationship and do like a stoichiometry problem with just volumes as well. So they sort of go up together, the moles and the volumes in this sort of relationship. It's like any other gas law. Obviously, you can plug and chug, into there and solve for any of those sort of values. So, including Avogadro's law, taking into account all those last laws that we talked about previously, Boyle's law, Charles' law, Avogadro's law, Lussac's law. We put them all together and we get basically the granddad of them all there, which is our ideal gas law, and that is PV equals nRT. And PV equals nRT is a really important gas law. It is different than all the other ones that we've seen up until this point. It is just a one-off sort of situation. It's not a before and after. So you got one pressure, one volume, one temperature, and one R there. And it's also the most restrictive in terms of units. So when you're using the ideal gas law, pressure has to be atmospheres. Volume needs to be in units of liters. N needs to be in units of moles. T needs to be in units of Kelvin. And the reason they all need to be in those units is R. R is the gas constant. And R has a value of 0.08206. And it has all those units, liters times atmosphere divided by Kelvin times mole. I personally use this number because that's what they beat in my head and I can't get it out. But a lot of times books will now round it to 0.0821. So you can use that number if you like as well. But that is a gas constant, and it is a constant value. It is a value that you always have available to you. So they won't tell you in a problem, hey, you need the gas constant. You just got to think about it as a value that you do have available to you. Any questions on that there? Yeah. That's the actual value of R. So that is, again, the value of R. And again, that's just a number that you should always have available to you. Usually never mentioned in a problem, never given to you in a problem. But if it's a sort of an ideal gas law, they just assume that you know that number and you have it sort of available for you to use. So if you're looking at the ideal gas law and you're doing a problem, you're like, I'm missing R, that's again a number that you should just have available to you. Other questions? All right, give me 1 second here. Okay, sorry about that. Okay, so our ideal gas law is something that we do use a lot. You do really the units, and it's something that people do sort of screw up on in a sense in terms of the units. Let's talk about a couple other important things that we also see with gases, and that is what is sometimes referred to as STP. STP stands for standard temperature and pressure. So when you're given a problem that says something like, hey, it's at STP, they're actually giving you values for temperature and pressure. So when it says STP, that means that the temperature is 273 Kelvin and the pressure is basically 1 atmosphere. So you actually do have values sort of given to you. when it mentions STP. Now, there's a really nice relationship that occurs when you are at STP conditions, and that is this relationship here, and it's only at STP conditions. 1 mole of any gas you have will have a volume of 22.414 liters. So that is a conversion, but it must be at STP in order to use that. Why would you maybe want to use that? It can allow you to not have to use the ideal gas law if you're at STP conditions. So you could kind of just use that conversion in a lot of cases and get the answer you're looking for. But you could still use the ideal gas law under STP conditions. You could just put in for the temperature 273 and for the pressure 1 atmosphere. So if you don't even want to worry about that conversion, don't worry about it. Just use the ideal gas law and put the numbers in, and you don't even have to worry about it. It'll come out the same. But it can, again, sort of allow you to not have to use the ideal gas law. But remember, so if your temperature is not 273 or your pressure is not 1 atmosphere, you cannot use that conversion. So it has to be STP only conditions to use that conversion. You could always use the ideal gas law for any conditions. So STP conditions, non-STP conditions, you could just throw everything into the ideal gas law, and everything will work. By the way, if we rearrange the ideal gas law and solve for R, using STP conditions, which means our pressure is 1 atmosphere, our volume is 22.414 liters, our mole is 1 mole, and our temperature is 273. That's essentially how we get the gas constant there that we use, the 0.08206 version of it. All right, so let's try one here. Calculate the pressure exerted by 1.82 moles of SF6 gas in a 5.43 liter container at 69.5 degrees Celsius. Pulling out the information, we're looking for a pressure, so that's a P. We have an N, which are moles. We have a volume, which is 5.43 liters. And we have a temperature here, which is 69.5 degrees Celsius. So again, you can see clearly we don't have 2 P's or V's or temperatures or any of those things. So that does eliminate everybody. This, again, would be the only one that really does make sense in terms of the information that was given to us. Because it does make sense, and we do need to use the ideal gas law, once again, anywhere in the problem. But now that I know I need to use the ideal gas law, I always have this number once again given to me. So that was just what I was talking about earlier. You just got to know that number and use it. So if we think about our P equals nRT, we have volume, moles, R, and temperature. So that's good. Moles are in moles. That's good. Normal here, our temperature is not in Kelvin, so we do need to convert it. So we'll add a 273 to that, and that's going to get us a 342.5 Kelvin. Now we have everybody in the right spot. It's not really written as a fraction, but basically we're going to move our volume to the other side and divide it over there, and it's going to end up on the bottom. And that would give us P is equal to nRT divided by V. Now we can put our numbers in, and we will get 1.82 moles, 0.08206 liters atmosphere Kelvin mole, our 342.5 Kelvin, all divided by our volume of 5.43 liters. Moles will cancel, Kelvin will cancel, liters will cancel. That's going to leave just atmospheres left over in terms of our gas constant unit, which is good because we're solving for a pressure. So we're going to take 1.82 times 0.08206 times it by 342.5, hit equals, divided by 5.43, going to give us a 9.42 atmospheres as our pressure in this particular case. Now, things that are very common in gas laws, especially like this, is a couple conversions that you might have to do, which is a lot of times you may have the volume in milliliters. So a lot of times you have to go milliliters to liters. And to do that right, there's 1,000 milliliters in 1 liter. So that's a very common conversion that you need to use. Also, you're not always lucky enough to get things in moles. Most of the time, I would say they would be in grams, and going from grams to moles, like we talked about in the previous chapter, that's going to be your molar mass, right, from the periodic table as your conversion factor, right, to do that. So those are two very common conversions, along with obviously the temperature conversion that you obviously has to do in a lot of these sort of gas law problems, especially with the ideal gas law, since it has those really specific units. Once again, if you're not sure the units, you probably will be given the gas constant there with the units. So you can just look at it and see what the units of everybody else needs to be in. Any questions on that one? Yeah.
To clarify, so
Oh no, so yeah, that was on either or either in that case. So yeah, they're the same. So personally, I use most of the time 0.08206, and that again is just kind of what I learned years ago. So it's just like in my head. But nowadays, a lot of books will use 0.0821, so I write it there. So you when you see it, you know it's a very common sort of rounding version of the gas constant these days. You can use either one that you like, but not together. So yeah, so just choose one or the other. Definitely don't use them together. Yeah. So this definitely right here is the gas constant, or if you do not use that number, you could use the other common sort of rounding version of it, which is that number there. Yeah. Other questions? All right. Well, I don't think we have enough gas laws, so let's add some more to the list here. There's still some room on paper somewhere. So let's talk about what happens when we do change pressure, volume, and temperature all together. Oh my. So if we take the ideal gas law and actually solve it in two situations for R, because R is a gas constant, that means that that value will be the same. And you could actually put these two things equal to each other because they equal the same number. But in most cases, when you have a problem, unless you open the lid, most of the time the number of moles of gas is probably not going to change all that much in a situation. So this brings us to a sometimes referred to as the combined gas law, which pretty much has everybody in it. And the combined gas law is P1 V1 over T1 is equal to P2 V2 over T2. And this is, I would say, a good one to know. Yeah. Yeah, along with all the other ones are good ones to know, but this is especially a really good one to know. Now, if you want to remember this version of it, it's really good. You could also remember this version of it, and it could be helpful as well. So I'm going to go with this version here and explain to you why it's going to be so helpful. So let's just take a look at that maybe here. And let's go this way, I think, maybe to look at it. So if I remember this sort of version of the combined gas law, where even I leave the moles in, I have something like this. So let's say you come across a problem and you're like, I do not remember all those other gas laws that we just learned. And maybe you do remember this one, which I would invest my time in remembering this one. And you see a problem and go, I do not have any temperature given to me. I don't have any moles given to me. Are they held constant? All you have to do is scratch these out. And now you have our friend Boyle's Law, right? Right there for you. Just scratch out what's not given to you or what's held constant. If you take this guy here and you come across a problem where maybe there is no pressure or moles given to you, you cross out the pressure, you cross out the moles, And dare I say, there's my friend Charles Law staring at you. Yeah. You take this guy here. And maybe there is no volume or moles given to you. You cross this guy out and this guy, cross out that guy and that guy. And there's Guy Lussac's law. Let's say you are looking at a problem and again, it's not given to you, or it's held constant pressure and temperature. You get rid of those. And there's our good friend Avogadro, right? So if you're going to invest the time, I would invest the time in this equation and pretty much just scratch out what's not given to you or what's held constant. And you'll have all the other gas laws we just learned: Boyle's, Charles, Guy Lussac's, Avogadro's. So really, if you remember this gas law, you could probably even leave out the N in most cases, but if you want to leave it in, you can. And you remember your ideal gas law. Between those two, you pretty much could have every gas law that we just talked about so far up until this point. Any questions on how to do that there? Yeah. So just a recommendation. You don't have to follow it if you don't want to. But again, it's a pretty good one because pretty much you get all the other gas laws from that particular gas law. Any questions on that there? So again, what you scratch out is what's not in the problem, are told it's held constant. Get rid of it, and then you have that. All right, so that pretty much just brings our gas laws down to only two that you maybe have to memorize and remember. And that's not too bad. Seems doable, I suppose. All right, so let's take a look at one here and see how our rearranging skills work. Consider a sample of oxygen gas at 27 degrees with a volume of 9.55 liters and a pressure of 2.97 atmospheres. We're going to change the pressure to 8.25. Okay, let's take a look. So once again, I'm just going to pull out the information. I got a temperature there of 27 degrees Celsius. I got a volume of 9.55 liters, and I have a pressure of 2.97 atmospheres. I have another pressure here of 8.25. And I have the temperature that's gone up to 125, and I am looking for a volume. So once again, just by labeling it like this, the combined gas law should really kind of jump out at you. You can kind of almost see it here. Once again, we could call the first set of numbers the ones, could call the second set the twos. It really, again, doesn't matter as long as you keep everybody together that goes together in terms of numbering. In terms of units, we have the same unit of pressure, so that's good. We need to do our normal conversion here of our temperature. So that's going to give us a 398 Kelvin and a 300 Kelvin here. Once again, we're ready to solve for it. So that's a P1 V1 over T1 is equal to P2 V2 over T2. In this case, we are looking to solve for V2, which means we want it by itself up on top, which it is. Now we just need to kind of get it by itself. So once again, the quick way is opposite locations. So that's going to go up, and this guy is going to go down, basically. And that will get us here that V2 will equal P1 V1 T2 up on top divided by T1 and P2. We're basically multiplying the T2 to both sides and dividing by the P2 to both sides is basically what we're doing. At that point, we want to put everybody in the right spot. So P1 would be 2.97 atmospheres. V1 would be 9.55 liters. T2 should go up on top, which is 398. On the bottom here, T1 of 300. And our P2, which is 8.25. Atmospheres on top and bottom will cancel. Kelvin on top and bottom will cancel. Gonna leave us liters there up on top, which is good since we're looking for a volume. 2.97 times 9.55 times 398 hit equals, divided by 300 hit equals, divided by 8.25 hit equals one more time, for a wonderful answer of 4.56 liters in this particular case. Yeah. Any questions on that one? Yeah. You didn't, because you got to also take into account the pressure. So you can't use Charles law. So you got to use a gas law that has all the variables in it. So in this case, since they had pressure, volume, and temperature, you got to use really only the combined gas law has all those guys together. Otherwise, you're not taking into account your calculation, the effective pressure on the situation. Other questions? I would say this is probably the one that gives people the hardest time rearranging. So if that's the situation, you should probably take some time just to, again, figure out how to properly rearrange it, because you may be asked to solve for obviously any of those things, pressure, volume, or temperature. So take a moment if you need to figure out how to rearrange. Any questions on that? So we're going to continue on here. Any questions so far on anything we've been talking about? So you are responsible for the gas laws, like I said, probably to make it easier. Just remember that one, and remember the ideal gas law, and you'll be in pretty good shape for anything that you need. We're now going to talk about what happens when we have a mixture of gases. So a lot of times gases do come as mixtures of gases, and that brings us to what is referred to as Dalton's law of partial pressures, which sounds super complicated. It's really not so complicated, just has a big name like that. But the idea here is this: if we have a container and pretty much the only gas molecule we have in that container is gas molecule A flying around, the total pressure of that container would be all a result of pretty much gas molecule A as it's flying around and causing collisions. Now, when we do get a container that has several different gas molecules flying around, A, B, C, I know my alphabet, that's good. And as they are flying around, when we think about the pressure of this mixture of gases, the total pressure of this guy is actually a result of the pressure caused by gas A, plus the pressure caused by gas B that's flying around, plus the pressure caused by gas C that's flying around in that particular container. These are what are referred to as partial pressures, because they each basically contribute to the overall pressure of the mixture. Now, one of the things that we deal with here is the idea that in most cases, we're dealing with what is known as an ideal gas. And one of the things that makes something an ideal gas is the idea of, although you may have multiple gas molecules flying around in the same container, in an ideal situation, they pretty much don't interact with each other. So it's almost like these gas molecules are in there by themselves. In an ideal situation, the presence of gas molecule B has no effect on gas molecule A or gas molecule C, even though they're flying around in the same container. And that's one of the sort of tenets of what makes something an ideal gas, is that sort of no interaction with other gas molecules. The other thing that makes something an ideal gas, as we'll talk about in just a second, is when we think about the volume of the gas itself versus the volume of the container it's in. The volume of the container is much larger than the volume of the gas molecule itself. So we think of the gas molecule's volume as being kind of zero, not important. And that's why in a lot of problems that you read when you're doing gas problems, they talk more about the volume of the container the gas is in rather than the volume of the gas itself. And in an ideal situation, that's sort of the two main things that make something an ideal gas. We sort of ignore the volume of the gas itself. We look more at the container it's flying around in, and we do not see any type of interaction between different gas molecules. So what is the simplest way and most common way that we could calculate the partial pressure? Well, frankly, we use our friend PV equals nRT. And we solve for each gas by solving for pressure. which would be nRT over V. You would solve for the partial pressure of A by just going into the ideal gas law. Again, everybody needs to be in the proper units like we talked about earlier. You would then do the exact same calculation for B, and you would do the exact same calculation for C. And then to get the total pressure, you just add them all together, basically, and that will give you your total pressure of that mixture of gases. Now, a couple of nice things about the mixture of gases is all these gases, they're all in the same container, which means they all have the same volume, right? Because they're all in the same container, they're all flying around in the same spot. My guess would also be that that container is sitting in the same room at the same temperature, which means they all have the same temperature as well, which means the only real difference when you use the ideal gas law in a partial pressure problem is moles. You just need to get the moles of each gas. Temperature will be the same for everybody, volume will be the same for everybody, and R is a constant, so that will be the same for everybody. So the only variable that will happen when you do this calculation 3 times, one for A, one for B, and one for C, would be the moles that you have for A, B, and C, and that's the only different thing that you would put into that equation. Any questions on that there? So that's, I think, what this says right here, pretty much. So, by the way, again, if you have 3 gases, you would just do it for each gas, and the volume, the temperature will be the same for everybody. So it really will come down to just getting the moles of each gas and just plugging it into the ideal gas law however many times you need to do it, and then add up all the pressures to get to your total pressure. All right. So with that being said, why don't you try one? We have 5 grams of helium and 5 grams of neon in a 2.5 liter container at 27 degrees Celsius. We are looking for the partial pressures of both gases and the total pressure of this mixture. Helium is on the periodic table there, 4.003. And neon, right? Yeah, neon, 2018. All right, let's take a few moments. You should end up with 3 answers. Partial pressure of helium, partial pressure of neon, and the total pressure of both of those guys together. So see what you come up with. Okay, let's take a look, see how you're doing. So basically in this situation, we got a container and we got helium flying around. We got a little bit of neon flying around. And we're gonna look for the partial pressures of each of these gases. So in this case, we do have the mass of each of these. So we have the grams, which we can convert to moles, which means we really do have N given to us. We do have a volume, which is 2.5 liters, and we have a temperature that's 27, which we automatically just an autopilot here. We'll convert that to Kelvin because I know that's where it's going to end up. So again, here, our ideal gas law would be definitely what we would want to use in this situation. Our PV equals nRT. We're going to solve for P like we talked about a second ago. And again, we're basically just going to do this calculation twice, one for helium and then one for, say, neon here. We probably should get our moles first here before we begin. So we're going to use our molar mass, which is 5 grams of helium. Use our molar mass from the periodic table here as a conversion factor like we did previously. We're going to go with the 4.003 on the bottom and the moles up on top. We'll also do the same thing here really for our neon. And we'll use the molar mass here of neon from the periodic table, which is 2018 grams per mole. And once again, just straight from there to periodic table. That's going to get us here for helium. Looks like 1.25, we'll call it. And for our neon, 0.248 moles. So we essentially now have our temperature. We have R, which is a gas constant we always have. We now have the moles and we have the volume. So we have really everything we need to solve for each of these gases using the ideal gas law. So we'll start with helium. The partial pressure here of helium is going to be nRT divided by V. So putting in the moles of helium, 1.25 moles. Remember, the gas constant never given to you usually in a problem, but we always have, again, that value to use. And that's what that is right there, our value of R. And we're going to do our temperature here in Kelvin. We're going to divide it by our volume, which is 2.50 liters. And that's going to get us here 1.25 times 0.08206 times 300 divided by 2.5. And that's going to give us, we'll call it 12.3 atmospheres. This number here would represent the partial pressure of helium in this particular case. Any questions on that so far? We're going to do the exact same calculation. Really, the only difference in the calculation is going to now be we're going to use the moles of neon instead of helium. Everything else is going to be the same because they're all in the same container. So we will then do our pressure here of neon. And it will be nRT over V. And once again, we're just going to substitute in our neon's moles, which is 0.248. Everything else is going to be identical here. And our 300, all divided by our 2.5 liters. And if we do that there, 0.248 times 0.08206 times 300 divided by 2.5, and we'll call it a 2.44 atmospheres. That would be the partial pressure of neon in this mixture. Now, the total pressure will be found by doing what? Yeah, I'm just going to add those two together. So we'll do a little 12.3 plus a 2.44. And we'll do a 14.7 atmospheres here as our total pressure. First off, any question on the calculation there? The major contributor to the pressure in this case is which gas? It is helium. Why is helium so much more pressure than the other one? Any ideas? It's exactly right. It's because it's lighter. Because it's lighter means it will have a higher velocity. It's flying around a lot faster because it's lighter. Going to cause more collisions and contribute more to the pressure than neon, which is heavier. Going to be flying around at a slower, what's referred to as a root mean square velocity. It's going to be moving around a lot slower than helium. Any questions on that? So this is probably a classic sort of partial pressure problem, which is really just an ideal gas law disguised in a partial pressure situation here. Any questions? All right, then there are a few other sort of partial pressure situations that do arise. Say you do an experiment like this. So you're going to do this, and if you haven't done it, you're going to do it today. Great lab. If you haven't done it, it's a terrific lab. All right, so you have a little potassium chlorate here, and you're going to do a little decomposition experiment there by heating that up, and you're going to use that as a catalyst to drive that reaction, hopefully a lot quicker. It's going to break that apart into a little potassium chloride, I'll spit that out, and a little oxygen gas, which is what we're trying to collect there. So typically you'll have a bucket of water here. You'll have a receiving beaker or whatever it may be there, a jar that has water in it. So as you do this, the O2 gets made, goes through, bubbles in, and water goes out, gas goes in, and in the empty spot in your receiving flask there, it's really not empty. It actually does contain the gas that you're interested in this particular case. The problem, though, is based on the way that we collected the gas, that's some water. And when you add a little bit of heat to water, you get water vapor as well. So you pick up another gas along the way, which you're really not interested in. It's just sort of a byproduct of how you're collecting the gas that you are interested in. So you get what's referred to as water vapor. And this creates now a partial pressure situation. And when you go to do a calculation, for example, you're not really interested at all in the water contribution. You're really just interested in the pressure of, say, the oxygen gas, which is what you're collecting. So in this particular case, the total pressure would equal the partial pressure of the gas you're interested in, or the O2 in this example, plus the partial pressure of water, which is also known as the vapor pressure of water. And that vapor pressure of water is typically a value that you could look up in a table based on temperature. So you could actually just kind of look it up 30 degrees, 25 degrees, and you get the vapor pressure of water. So when you would want to go on, for example, to do a calculation that would involve the pressure, you would want just the pressure of the gas. By the way, in the laboratory, your total pressure is your barometer reading, right? I guess I shouldn't write barometer reading there. So the barometer reading is what you would use as your total pressure in an experiment. Do you guys have the mercury barometer still in the lab? You guys even look at the barometer? No? Oh, then don't worry about it. You didn't heat it either? Just look. They might have changed it over the years. It's been a long time since I've done it, but I wasn't allowed back in afterwards. I know. Got to scoop a ton of that MnO2 in there to get it going. So in this case, you would actually find the partial pressure of the gas you're interested in by taking the total pressure and subtracting off the vapor pressure of water. So a lot of times this type of partial pressure problem is used a lot in labs as sort of a correction calculation to get rid of basically the water's contribution to the pressure, so that what you're left with is, sometimes people refer to it as the pressure of the dry gas, because you're kind of subtracting off the water's contribution to the pressure. Any questions on that one there? Yeah. Yeah, so there's usually a table, and it's the vapor pressure of water table, and it's usually based on temperature. So you would do your experiment, get the temperature, which you typically would do in a gas experiment. You go to the table and just find what the vapor pressure of water was at that temperature, and you basically use it. Is this really more of like a correction calculation when you do a sort of an experiment like this? And the reason we have to do this is, in a lot of cases, that's a very common way that we collect gas, sort of like have water and to kind of displace the water and collect the gas in its place. So a lot of times when we just, the process of collecting the gas, we get this extra water vapor that we're not really interested in. That's sort of a byproduct of how we did it. So if we look at a problem like this, a sample of oxygen gas is saturated with water vapor at 30 degrees Celsius. The total pressure is 753 torr, and the vapor pressure of water at 30 degrees is 31.824 torr. What is the partial pressure of oxygen gas in atmospheres? So when you see a problem, and there's kind of a couple of keywords that you sometimes will see in problems that tell you this is the situation that's happening, this sort of vapor pressure of water. This is one of the keywords, like saturated with water vapor. That's a key of like you got some extra water in there you don't really need. You just did something like that. Or something that mentions like you collected the gas over water. So some type of mentioning of you got your gas collected with water involved, or over water, or with water. Those are common sort of words that tell you this is really this situation that we just talked about that's happening. This value right here would be, as we were just talking about, basically you would go to a table, and since this was done at 30 degrees, you would go to that table and look up the vapor pressure of water at 30 degrees, and that would be the number that you would see there, 31.824. So what we have here is the total pressure is equal to the pressure of oxygen gas plus the vapor pressure of water. And we know the total pressure was 753 torr. The pressure of oxygen we're interested in. And once again, we get this typically from a table is where we find that. And again, that is what that value is from right there. And we would use the 31.824 torr. The good news on this is basically just a subtraction problem, right? So we're just going to subtract the 753 minus the 31.824 torr, and that will equal our partial pressure of oxygen. And in this case here, we will end up with 721 torr is our partial pressure of oxygen. And so again, sometimes in labs and stuff, they refer to this as the dry gas pressure there. We also want to convert it to atmospheres, which was the problem. So once again, remember that 1 atmosphere is equal to 760 torr. And that means that we would take our 721 torr. We're going to divide by 760 here to convert it into atmospheres. And that will get us 0.949 atmospheres. So this is a second sort of partial pressure situation that really does occur a lot in sort of labs that you do. And again, it's really just a result, as I mentioned, a byproduct of how you're sort of collecting the gas, and you're sort of correcting your calculation by getting rid of water's contribution. Any question on that as well? Yeah. You could, if there wasn't that last sentence in this one where it says give it in atmospheres, you could just left it in torr. It could be, yeah. And by the way, this sort of concept also works, for example, you know, if you had a problem where it said, hey, your total pressure was 790 torr, and it was a mixture of, say, oxygen and whatever, helium, right? And they're like, hey, the partial pressure of oxygen was 700 torr, right? What's the partial pressure of helium, right? Basically, in this case, the total pressure would equal the partial pressure of oxygen plus the partial pressure of helium. And in this case, we would have 790, and we're looking for our helium. And we know that this guy is 700 torr. So you could do it, you know, just like if you had a partial pressure and a total pressure and you're like missing somebody else's partial pressure, you would just subtract it as well, right? Because it should add up to the total pressure as well. So it's kind of the same idea as well. So that's sort of a third way that sometimes you'll see a partial pressure problem, where they might give you a partial pressure of one of the gases or two gases, depending on how many gases you have in the mixture, and ask you to find the partial pressure of another gas, but also give you the total pressure. So in that case, all you have to do is just subtract off from the total pressure, and that'll get you whatever's left. So my bad example here, 90 torr, right, would be the partial pressure of helium. If we subtracted 790 minus 700, that would give us our partial pressure there of helium in this example. So you could also apply this in a non sort of vapor pressure situation, but you just have a bunch of partial pressure gases. Any questions on that? So let's talk about the kinetic molecular theory of gases. We've hit some of these points along the way. Gases consist of tiny particles, which are atoms or molecules. The particles are small compared to the distance between them. So the volume of the individual gas molecules are assumed to be negligible or zero. As I mentioned before, that's basically one of the things that makes something an ideal gas is we're not going to really worry about the volume of the gas molecule itself, but really the volume of the container is more important in terms of that relationship. Particles are in constant random motion, colliding with the walls of the container. This is what we see with our gas and our pressure going up. As we have a greater number of collisions, we will see pressure increase. As we have less number of collisions, we will see the pressure go down. Particles are assumed not to attract or repel one another. That is the second really thing that makes something an ideal gas. And that is why when we did our partial pressure sort of calculations, we were able to just basically assume that they were in there by themselves. And we could just basically do separate calculations for them. The reason why we don't have to worry about them sort of interacting with one another, or if we did worry about them interacting with one another, and it would be this idea: if we had a gas molecule that was heading towards a wall and going to collide with it, but it was actually attracted to another gas molecule that's behind it, it would slow it down, and that would cause a difference in the pressure that we would see in a non-ideal situation. Non-ideal situations, which are sometimes referred to as real gases, occur under really high pressures and really low temperatures. So you got everybody in a very small space. They're around each other for a really long period of time. And you do have to take into account how the gas molecules interact with each other. And you do have to take into account the volume of the gases. The good news is we don't do that in this class, and it makes the ideal gas law turn into what's known as the van der Waals equation, which is a scary looking version of the ideal gas law. So we don't do that in here, so we don't have to worry about it. Everything in here will be an ideal gas in most situations. As we talked about, if we increase the energy, we will increase the average temperature of the gas, and that will cause everybody to start moving a lot faster and affect either the pressure or it may affect the volume as well. These are just some of those relationships that we talked about through the different gas laws. Again, at high temperatures, gas molecules are moving faster, hitting the walls of the container, and we would expect at lower temperatures, they're moving a lot slower. The pressure temperature relationship, as we talked about with Lussac's law, in a rigid container, that volume is not going to adjust, which means as we increase the temperature, we will see the pressure start to increase. And as we lower the temperature, we will see the pressure start to come down. And again, that is different than what we see in Charles' law situation, where the volume's able to adjust to allow the pressure to remain constant. Any questions on any of that stuff there? That is chapter 8, I believe. Yeah. All right, we're going to go off to chapter 9 here next. Let me just get that up there for you. Chapter 9, which is solutions. We're edging closer to organic chemistry, which I don't know if that's a good or bad thing. We'll see. Bad thing for me. I don't like organic, but I'm just kidding. But we can put our calculators away when we get to organic. We just toss those in the trash can. But we do have to pull them out of the trash can for exam 3 because there's calculations, but no calculations when we get there. All right, but definitely calculations in this one. So let's talk a little bit about solutions. Most important biological reactions do occur in an aqueous environment. Aqueous environments are those guys that have the AQ symbol next to it. It's basically a solution. And a solution is a homogeneous mixture, which means that everything looks the same throughout. And there's really 2 parts to a solution. There is the solute and the solvent. The solute is the smaller part of the solution. The solvent is the larger part of the solution. So for example, a reminder as well before we get there, there is a difference between L and AQ. L is a pure substance like water. Aqueous is again a solution or really a mixture. So when you take something like water and sodium chloride, as we talked about previously, and put these together, we get a sodium chloride solution where the sodium chloride is the solute and the water is the solvent in this particular case. How do you know what is the solute? Is the name of the solution. So if you have a sodium chloride solution, sodium chloride is your solute. If you have a potassium nitrate solution, potassium nitrate is your solute. So whatever the name of the solution is the solute. If it is an ionic compound, it most likely will be water's the solvent. Water is a very good solvent for ionic compounds because they mix really well together. So typically ionic compounds will dissolve in it. Like if we took salt and water, the salt will dissolve in the water with no problem. And it's able to do that, as we might have talked about, and we'll see, essentially, if we took something like sodium chloride in solution, you would have sodium ions and chloride ions floating around. And as we know from bonding, our friend water is a polar molecule where oxygen is more negative and hydrogens are more positive. So how we dissolve something is essentially water molecules start to surround these ions. So the negative side of water, which is the oxygen, would surround like the sodium ion, while the chloride ion would actually be surrounded by the hydrogen side of water. And that's essentially how sodium chloride dissolves in water. There is no chemical reaction that occurs. It's a physical change. We just visually cannot see it anymore because we threw a ton of water molecules all over it and it's hidden inside the water sort of matrix. We no longer can visually see the sodium chloride in it. We know it's there because you probably did this at some point. or maybe next week you'll do this. If you take some salt water and you heat it up, all the water is going to evaporate, right? Which means now there's nothing in the way of those two ions from coming back together, and you will see the solid reform. So it's always been there, it's still there in the water part, but you just can't visually see it. We also get things to dissolve because typically when we take something like an ionic compound like sodium chloride and we go to dissolve it, we typically start to stir, yeah? And when we stir, we're throwing a bunch of water molecules on our ionic solid. By the way, ionic solids are pretty much just a three-dimensional structure of ions bunched together. So when you throw all these waters on there, and as you stir, you're also creating some energy. That's going to allow the dissolving process to occur a lot faster. Also, why sometimes if you're trying to dissolve a solid and it's not dissolving, they sometimes will tell you to warm it up a little bit, right? Warm it up a little bit, you get a little bit more energy, get things to start breaking apart and starting to dissolve as well. So here's a water and a copper 2 sulfate, and this is our solute. That is our solvent. And obviously, as we start to mix it, these guys get all mixed around. And now we have a nice blue solution, which is aqueous type of guy there. So as I mentioned, water is a really good solvent for things that are polar and things that are ionic. It's a pretty crappy solvent for things that are nonpolar because nonpolar things have no charge. And nonpolar things like to use what is known as dispersion forces as their main route of interacting with other molecules. And these are like really weak interactions. And that's very, very different than what water likes to use. Something like water likes to use what is known as hydrogen bonding between the negative side and positive side. That bond right there, which is known as hydrogen bonding. So because water likes to use hydrogen bonding and nonpolar things like to use dispersion forces, they cannot basically interact really well with each other for a long period of time. Hence why when we put oil and water, do they mix? They don't, because oil is pretty much nothing but a long chain of nonpolar carbons and hydrogens all together, and it's quite big. And when it tries to interact with water over the long period of time, they have no way to maintain that interaction, because with dispersion forces, they typically are kind of like temporary type forces that allows them to interact with one another. But if something changes, there goes that sort of way that they can interact, and it kind of breaks apart and has to reform new ones. And that's different than how polar molecules or ionic guys do. They always have a charge no matter what you do to it. No matter what you do to water, it's always got a positive side and negative side that will never change. And it's always ready to go to bond and interact with other molecules. Something that is nonpolar like oil needs something to happen. It needs this like electrons to start moving around to get us temporarily charged so it can kind of interact. Because all interactions between molecules and other molecules, they all interact basically the same way. They all interact by a very simple interaction of positive, negative attraction between them. So the negative side of one molecule is attracted to the positive side of another. And the problem with nonpolar molecules is they're neutral, basically. They have no charge. So they can only temporarily get a charge to help them interact, but they need something to happen for that to occur. So that's why over the long period of time, it doesn't really work well. As we'll see in this chapter, the idea of what's referred to as like dissolves like, things that use similar types of interactions that the molecules use with themselves will always be soluble with each other. So other things that use hydrogen bonding are very soluble with water because it's the exact same interaction that water uses with itself. And even nonpolar things are actually quite soluble in other nonpolar things, because other nonpolar things are using the same interaction. They're also using those dispersion forces, so they're able to interact well with one another. So sometimes people forget about that interaction. Nonpolar things are actually soluble in other nonpolar things because they're using the same sort of interaction. Any questions on that there? Here's a picture of that, almost like I drew, if you close your eyes. That's basically the water molecules coming in and nicking it off. Here's another picture of that in case you didn't like that first one. And a third picture in case you didn't like the second or the first picture of that happening. But all those are pictures of water coming in and basically the dissolving process and surrounding each of the ions. Again, you can see here, this is the hydrogen side, and that is obviously the oxygen side there. Now, solubility in water, as we sort of just talked about a little bit, ionic compounds are definitely always going to be soluble in water because of that sort of interaction. It's able to work really, really well with water's sort of dual side, a positive and negative side. So it works well with positive and negative ions. So non-ionic compounds, though, are also sometimes soluble in water. So if we take something like sugar or ethanol, this is ethanol. Speaking of organic, when we get to alcohols. If I draw it correctly, that would be even better, probably. There we go. That's a bad C right there. All right. So this is basically ethanol, and it has really kind of two parts. It has all these carbons and hydrogens, which is kind of a non-polar part of it. But it does contain this OH bond, which based on electronegativity difference is going to be a polar bond. It's going to be actually more negative on the oxygen, more positive on the hydrogen side because of the electronegativity difference, like we talked about with bonding. And when we get something like water that comes through here, it's not going to have any problem in this case interacting with ethanol because, surprisingly enough, it has the exact same bond. It has that OH bond, which is exactly the same bond that it has in ethanol. So that interaction right there, which is known as hydrogen bonding as well. By the way, in order to have hydrogen bonding, you need what element? You know, hydrogen, by the way. But it need a special hydrogen. The hydrogen needs to be bonded to a nitrogen, oxygen, or fluorine. So just because somebody has a hydrogen doesn't mean it can actually hydrogen bond. It has to actually be a hydrogen that is directly attached to nitrogen, oxygen, and fluorine. As I go with electronegativity, what are those three elements? Those three elements are one of the most three electronegative elements you could have, right? Electronegativity increases as you go up and to the right. This three-pack of electronegativity means when it hooks up with something like hydrogen, you're going to create a quite polar bond, which is going to give you that separation of charge, a positive side and negative side, which is necessary for that interaction to occur. There is a limit to this, though. If you were to add on a bunch more carbons, maybe something like this, 1, 2, 3, 4, 5, 6, 7, 8, 9. Let's just stop at 9. And we'll put an OH group on it. And all these are hydrogens. I really should have stopped at 6. We'll save the naming for when we get to organic. All right. But now when we look at this guy, you have quite a big part here that's non-polar, right? And we have just this little part over here that's polar. Pretty much no solubility at this point because too big. Yeah, sometimes referred to as steric hindrance. This big non-polar part gets in the way of water being able to get in there and interact really well. Remember that for something to dissolve in water, it has to replace water and water interactions, right? Because before you dissolve something, you got a bunch of water molecules attached to each other. And you got to break off some of those and let some other things in. Water is a relatively small molecule. So when you drop something like that, kind of big, only a really small spot that it's able to interact with, pretty much no solubility at that point, even though it has that OH group. So usually in these types of situations, if you hit about 6 carbons or so, that's pretty much where you see your solubility pretty much drop off to not so much. But up to about 5 carbons or so, you'll have pretty good solubility. Also, if you put a bunch more OHs all over the place, that will also increase the solubility because now there's a lot more places for those guys to interact with water and stuff like that. So those are some factors that can affect it. When we have something like sucrose or sugar, it's a relatively large molecule as well. but it does have a bunch of OH groups littered all over it. And everywhere there's an OH group, it gives it an opportunity to interact well with water. So it really increases the solubility of something in water. This is methanol. Again, a smaller organic guy, and it has that OH group, which is able to hydrogen bond pretty well there with water. So it would be soluble in water. Here's our ethanol doing its hydrogen bonding as I just drew there. Now, oil and water, as we just talked about a second ago, again, they really do not mix. And the reason, again, for that is, as we'll see a picture of it, pretty much it's just a long chain of carbons and hydrogens. Like gas is octane, that's like 8 carbons. Yeah. And that's how they get all those products. Big long hydrocarbon chain. They do cracking of it, just breaks them off into smaller chains, and you get different sort of products out of it. But because it's really big and it's using that dispersion forces versus the hydrogen bonding that water wants to use, it's just not going to work. And as I mentioned before, it's a relatively large molecule that doesn't have any type of interaction that works really well. So I usually sometimes think of it like a garage, right? You get a car in there, nice, right? Fits, door shuts. Park a semi truck in there. You could probably get part of the truck in there, but it's not going to fit right, right? It's not going to work really right in your garage. And you might take out half your garage with it as you try to pull that thing in there. So just because of the size of it, it's not going to work really, really well. So this brings up the idea of like dissolves like. So if you have something that is ionic and you have something that is polar, that's all going to be good. That's all going to be soluble in each other. If you have something that is polar and polar, that's going to be soluble in each other. If you have something that is nonpolar and nonpolar, that also would be soluble in each other. You really only run into a problem when you kind of cross over into the polar and nonpolar situation. Not so good, not going to be soluble in each other. Again, because they're really using different forces. Will things be able to, in a short period of time, kind of work together? They can, right? Oil and vinegar salad dressing, right? Mix it up. Stays mixed for a bit, but once you put salad dressing down, eventually will separate out, right? And again, is because they cannot maintain that interaction over a long period of time. Every single thing could actually use dispersion forces, which is why things can interact for each other for a short period of time. But over a long period of time, they have no way to maintain that interaction. And again, like the salad dressing example, you know, things will just sort of separate out. Also, why if you have an oil spill in the water, right? You see it floating on top, right? Because they don't mix. And usually the organic stuff, like oil, is on top. The water stuff's on the bottom in terms of their densities, and that's where they sort of end up. Any questions on that there? All right, so here's a picture of sugar, but although it's a larger molecule, you can see it is pretty much littered everywhere with OH groups. And again, that's going to definitely increase the solubility with water. And this is typically what oil looks like. And as you can see, it's all carbon-carbon bonds, which are nonpolar, carbon-hydrogen bonds, which has electronegativity difference of 0.4 and being nonpolar as well. And again, just very, very different interactions. So they don't interact well. They usually end up something like this, where we have the oil up on top and our water layer there on the bottom. Now, solubility, when we talk about something being soluble, when one substance, the solute, dissolves in the solvent, it is said to be soluble. So salt is soluble in water. When they do not dissolve, it is insoluble in water. There is a limit to solubility, and it's based on temperature. You can, for example, take a little bit of sugar packets, right, and get it to dissolve in a glass of water. But if you pull out the Costco size thing of sugar and pour it into your glass of water, at some point, it's not going to dissolve, right? It's just going to kind of pile up on the bottom. So there is a limit to solubility. And a lot of times with a solid in a liquid, temperature plays a role. As you increase the temperature, you could get a lot more solid to dissolve. If you lower the temperature, you typically get a lot less to dissolve. Gases are always soluble in each other, and that's because, frankly, they are flying around, right? So they're constantly mixing, so they're going to mix well with each other. Some liquids are also mutually soluble in one another. So polar and polar, nonpolar and nonpolar will be soluble in each other. That is a solubility table and also the signal of, we should lay it up here right at this point, I think, for today.